Hi everyone. So we'll start with our discussion of differential amplifiers. But before we go to the understanding of differential amplifiers, I'll give a quick historic perspective of what we have discussed so far. And also you'll understand one of the needs or one of the motivations for going to differential amplifiers. So to do that, I'm going to start with the discovery of electric bulb. In 1880s, Edison perfected the idea of an electric bulb. So this electric bulb works on the principle of it's an incandescent electric bulb. So you heat a filament by applying a large voltage across it. The I square R losses, it's going to heat the coil. And when it heats this filament, it's going to emit out radiation in the visible spectrum. So that phenomenon is called incandescence. Now Edison perfected this invention, though the invention itself is not his, but he perfected this invention and made it a household product. So that's where the credit actually is still given to Edison. Now one of the problems that the electric bulbs were facing at that point was that as the bulbs were used for over a longer duration, a soot from this filament material was getting deposited on the walls, the transparent glass of the bulb, and this was creating some kind of a shadow effect. So it was creating some kind of a shadow in the light of your incandescent bulb. So Edison, being the great tinkerer that he was, so what he did was he introduced a metal plate inside the bulb in the hope that the metal plate will attract all that soot material. And he made an interesting observation that when he applied a certain voltage to the metal plate, where such that the voltage of this metal plate is always higher than the voltage of the coil or the filament, then he noticed a current flowing in this path. At that time, you should understand this was in 1880s, around mid 1880s. So the idea of electron itself didn't exist. So they didn't understand what was happening here. So J.J. Thomson's discovery of electrons in cathode ray tubes happened at a much later time. So this was in 1890s, late 1890s is when J.J. Thomson discovers the electron. That happens across the Atlantic. So Edison was in North America and the discovery happened on the British side. And so Edison he didn't have a theory or mathematics to understand what was actually happening. So this phenomenon, when they introduced a metal plate and held its potential higher than the potential of the filament, and suddenly a current was flowing, that effect was called as Edison Effect, and it was also replicated by scientists of that time. But there was no good understanding of it. Then came early 1900s. So that is when the other scientist on the other side of the Atlantic, so from John A. Fleming, he started experimenting with the same Edison effect, and he discovered an interesting phenomenon that if you apply a positive voltage, where the voltage of the plate is greater than the voltage at the filament, if he could somehow maintain that, then current was flowing from the metal to the voltage source. The current was flowing in this direction. So he was noticing current actually flowing in this direction. And when he applied a negative voltage, so when he maintained the filament potential lower than the voltage across the filament, then he noticed there was no current. So it was behaving like an open. So he called it a valve. Like a valve, he could control the flow of current. He could have current or no current. So he called it as a valve, which would later evolve to become a diode. And he gave a simple physical explanation that he said the phenomenon of incandescence. So when you heat the filament is emitting out electrons. So this was in early 1900s. So by then they had an understanding of what an electron was. When Edison saw the Edison effect, at that time a lot of scientists still contested the idea of an atom itself. So electron is a much distant dream. So therefore he didn't have the necessary physics or the physics at that time to give an explanation for Edison effect. But Fleming, on the other hand, since he performed these experiments in early 1900s, he had the theory for it. And his explanation was that this metal the filament was emitting out these electrons. And if you maintain the plate voltage higher than the filament voltage, then these electrons were drawn towards. There was an electric field which was drawing the electrons closer to the metal plate. and so there was a flow of current. So electrons move in this direction, so the flow of current is in this direction. And in the other case, when he maintains a negative voltage on the plate, the electrons were repelled off, so they had no path, no current path existed. So this was one of the earliest inventions of a proper diode, vacuum tube diodes. So just to quickly point out, the idea of rectification, meaning current flowing in one direction, did exist around the same time, because at that time, early 1900s, is when Marconi had developed the radio sets, which was used for wireless telegraphy. And not the radio sets. Radio didn't come into existence. It was mostly the wireless telegraphy was becoming more and more popular. So though they didn't coin the term diode yet, but it was called cat whiskers. So it was the simplest semiconductor and a metal junction. So this is, on the other hand, this also behaves like a diode, but this was built using vacuum tube. So this was the earliest vacuum tube diodes. And Fleming called it as valve. And also, just to quickly point out, it made sense to call it as a valve, like a valve, by an application of a voltage, which is by the movement of a tap, he could control the flow of current or flow of water between 2 points. So he could control the flow of current between 2 points. So he called it as valve, but later diode, vacuum tube diodes were more popular words that were used for those devices. Then came in the late 1900s, so this was in the next half of probably in the decade of after 1905, another scientist in North America had introduced, what he did was, extending on this idea, he just introduced another terminal, a third terminal called the grid terminal. In between, this terminal was by then called anode and cathode, and he introduced a third terminal in between. And what he observed was, by introducing this third terminal, he could actually control the flow of electrons. Of course, this plate here, the anode plate, is always held at a higher voltage than the cathode plate. The cathode plate is a plate which generates electrons. So I had already explained this, but any amplifier, all the three terminal devices which we have discussed so far, which is MOSFET, BJT, or a vacuum tube amplifier, has one terminal which generates carriers. It can be electrons or, for example, once we came to semiconductors, it could be both electrons or holes. But you need one terminal to generate carriers, other terminal to attract those carriers, and a third terminal to control the flow of carriers between these two terminals. So then most of these amplifiers can be summed up by that simple explanation. So he introduced a third terminal called the grid terminal. And by applying a voltage on this grid terminal, he could control the flow of electrons or the flow of current between the anode and cathode, or flow of electrons between cathode to anode. And this was patented in late 1900s. So this was after 1905. So in that decade itself, this idea was patented. But a lot of, if you read about the history of radios, a lot of scientists at that time claimed that he didn't have a full understanding of what was happening in the device. He was again more of a tinkerer, kind of an innovator, but it took effort of other engineers to physically explain it and extract useful amplification out of this device. So all you needed to do was replace this current measuring device with a resistor here, so which is what I've shown here. Then the voltage across this resistor, so because this current here, the current here was proportional to the grid voltage, and if you apply a small signal voltage Vi on top of some bias voltage, then the current flowing here from anode, for the current flowing in this direction from anode to cathode, was proportional to the grid voltage, or which happens to be the small signal input voltage. And if that current flows into a resistor, the voltage drop across the resistor will be proportional to the input voltage. And then they had an amplifier built out of it. So this was in 1910s, where a practical amplifier using vacuum tubes was built. And for next 4 decades, vacuum tubes completely ruled the telephone industry. Long distance telephony became a possibility because of vacuum tube amplifiers. High power transmitters, computers, the earliest form of computers, they were all built using these vacuum tube amplifiers. But then vacuum tube amplifiers came with one major problem, that you had to burn a lot of heat to generate those electrons. The source, the electron which were generated by the source, the method was what we called as thermionic emission. And for that to happen, we had to heat the coil to really high temperatures. And because of that, a lot of power was wasted. And they were bulky, and like any bulb, they were also getting burnt out. So obviously they needed a better solution, an amplifying device, but a better, more compact amplifying device. And in 1940s, in fact, a proper junction transistor was fabricated in early 1950s. That happened to be a bipolar junction transistor, which came as an outcome after the invention of point contact transistor in 1947 at Bell Labs. So then the whole amplifiers completely revolutionized the electronics industry. Now that's where till this point is what we discussed from a historic point of view. And we discussed what are the different ways in which we can build amplifiers using MOS and bipolar junction transistor devices. Now from this lecture onwards, we are going to discuss a new kind of architecture, a new architecture of amplifiers called differential amplifiers, which started the idea of the differential pairs existed even during the idea of differential amplifiers existed. I'll define what differential amplifiers is soon, but I'll just say that the idea of differential amplifiers existed in 1930s and 40s, but it gained a much greater momentum after the IC technology was perfected. So today we use the devices, the very popular analog circuit called operational amplifier. So that's one classic example of a differential amplifier. So what exactly is differential amplifier? To explain that, I'll use one of the standard ways of explaining it, which is to start with a noise which is present on the supply. So generally so far, when we drew or analyzed amplifier circuits, we assumed that there is a DC voltage available to us. But then in practice, where is this DC voltage actually extracted from? Now either we can have a battery, but eventually you have to somewhere charge that battery. So where does that energy to charge the battery comes from? So now we are in 1920s. So that's when after this, 1920s is when vacuum tube amplifiers had gained its popularity. Now at that time, you should also understand that most of the power that was actually transmitted in the houses, the household power which was transmitted that was actually available in every house or in every working place was an AC power. So in 1880s and 1890s, there was this huge AC versus DC war, and finally the world settled, or in fact North America first settled for AC, because AC could be transmitted to longer distances with much lower power losses in comparison with DC. So this was the problem in 1880s. By using transformers, they could ensure the power losses were minimized when we go for an AC transmission. So AC was completely popularized. Now, if you are receiving an AC voltage to the house, then how do we derive a DC voltage from it? How do we derive a DC voltage in a house or a lab, which can then be used to power an amplifier? So this again is something that's a circuit from very basic electronics. So we use what we call as diode rectifiers. So these are the circuits which can convert. Of course, there are far more advanced and more interesting AC to DC converters now, but I'm talking about a very simple generic DC to AC to DC converters, which are the diode rectifiers. So a diode allows current to flow only in one direction. So if you apply the sine wave to a diode, then at the output what we will receive, it will look like, so this circuit what I've drawn here is a peak detector. So I'll assume the diode's cut-in voltage is 0. So then the diode will turn on whenever the input voltage here is greater than this voltage. If I assume initially you're starting from 0, the output voltage will also track the input. So this is the input voltage. The output voltage is also going to track the input. And after a point when the output reaches the peak value, when the input goes lower than the output, the capacitor can store the voltage, so it's going to remain constant. So it was called as a peak detector. But now in any practical circuit, you're going to draw some energy, you're going to dissipate some power. So that energy from the capacitor which is stored will be dissipated across a load resistor. So what will happen is that the voltage will slowly start getting discharged through the resistor. But this diode will get activated again when the input voltage, so this is the input voltage becomes greater than the output voltage. So it will do something like this. So you will have a voltage and some kind of a ripple at the output. Now the output voltage here, the input voltage, the average value was 0 because we fed a sine wave. On the other hand, we have an output voltage which has a finite average value. So we have an AC to DC conversion. A more complex system would look something like this. This is a typical AC to DC converter. So for example, let's say I need something like a 5 volt or a 5 volt DC signal which I am going to use to power my amplifier. Then the input, for example, in Asian countries we have 230 volt or 220 to 230 volt peak AC signal available at the house, from the grid or from the power supply, and the frequency of this will be 50 hertz. So in North America it will be different, it's around 60 hertz, and the value of the AC voltage will also be different. So this signal is first converted to, first we need, if you look at the peak detector circuit, the peak value that this can go to is simply equal to the peak value of the sine wave. So I need a peak detector circuit to convert a sine wave to a DC signal, but the peak of that sine wave which I am going to feed to the peak detector should be equal to the DC value or close to the DC value that I need to generate. I need to, from 230 volt peak signal, I need to convert it to a 5 volt AC signal with a 5 volt peak AC signal. To do that, we will again just use a transformer. A transformer with an appropriate turns ratio. So here it's n:1, though the secondary turn voltage will simply be V1 upon N. So we can choose an appropriate turns ratio to get that voltage at the secondary of the transformer. This is fed to a diode rectifier circuitry. So this is in fact a full wave rectifier. I'll not go into the details. So all a full wave rectifier does is that it converts a sine wave which can go both positive and negative to a sine wave which will have only one polarity. So it will have a finite DC. So if I pass it through a capacitor and all of that, the waveform will look something like this. So it will have a small ripple because we are generating it from a AC signal. It will have a small ripple and a DC value. So it will have a DC value and a small ripple around that. And the frequency of the ripple, in case of a full wave rectifier, it's going to be 2 times the frequency of the input sine wave because it's a signal of frequency 100 hertz now. So this will be a full wave rectifier output will be of frequency 100 if I start with 50 hertz. So all I have now is that I'm going to feed this 5 volt as an input to the amplifier, but it's also going to come with a ripple, some unwanted component on the supply. Now mind you, this is 100 hertz. Now if I'm going to use this in an amplifier, use this as a supply for an amplifier which is going to amplify a speed signal coming from a microphone. So let's assume I'm going to feed a pure harmonium as an input to a microphone, and harmonium is a device which can generate perfect sine waves. So it can generate a pure sine wave as an input to the amplifier. Ideally we would expect, so this is a common source amplifier, ideally I would expect the output to simply be equal to minus of GMRD times the input. So that's what you would expect here. So that's what I've shown here, an amplified version of the input signal. But then you have to keep in mind here that the DC voltage here, it's not just a fixed value, but it also has some kind of high frequency signal riding on top of it. So now I have 2 AC signals in this system. One is the AC signal from the supply, which is because of the AC to DC conversion, and also the AC signal which is your microphone signal, which is the intended signal to be amplified. Now we just found out the transfer function for the input signal, which happened to be minus of GMRD times Vi. So that's the small signal voltage gain of this amplifier. I've assumed R0 as infinity. So that's what you're going to get. But we will also have some component from Vn. So if you see in the circuit here, so I'll try to derive what is the transfer function from the supply. So that will be VDD plus VN. So I'll assume a small signal, so I'll ignore VDD. So the small signal variations here are only due to VN. And at the input, since I'm trying to find out the contribution from VN to the output, so I'll assume I'll apply the principle of superposition. So therefore I'll make Vi as 0. So gate is going to be at 0. The small signal wise, the gate is going to be at 0. So now if you see, if let R0 be the output resistance of this MOS device, the V0 here will simply a potential division from R0 and RD here. So it will be R0 by R0 plus RD times Vn. If I assume R0 is infinity, this will be just Vn itself. So which means your signal, which is the supply noise, is entirely going to appear at the output. So it's going to appear, the signal you are actually going to have here will be minus of GMRD times Vi plus Vn. So this is the unwanted supply noise. Now if this supply noise, the frequency of the supply noise, if you use a full wave rectifier to derive the DC voltage, the frequency here will be in around 100 Hz. So that's 100 or 120 Hz. Now this frequency falls within the audible range. So therefore you can actually hear this noise as a humming noise. So this is called the supply hum. Now this is something that's unwanted. And in fact, the earlier circuits also used to have some kind of feedback mechanism, especially RF circuits and radio frequency circuits. Now because of which sometimes the supply signal used to get amplified by a much larger factor, and that resulted in a larger humming noise coming from the supply. Now is there a way to fix this? Is there a way to reduce this supply noise? By doing some manipulations on the circuit. So that's what we'll try to answer that, and I'm just telling you that differential pairs is an answer to that. So to do that, I'm going to take two identical amplifier circuits. So you have a MOS device, two identically biased MOS device and two similar resistance values. And I'm going to bias both these amplifiers using the same supply voltage, VDD, the noisy supply voltage, which is VDD is the supply voltage and it has some supply noise riding on top of it, a 50 or the 100 Hz or a 120 Hz noise. And I'll also ensure the grounds are also same. Just to quickly mention another point. Now let's assume there was some noise on the ground terminal. I haven't analyzed what happens, how does it appear at the output. I'll call it VGN as the ground noise. So to analyze that, I'm going to assume the other two noises, the supply and the input signals are 0. So we'll see what is the contribution of this ground noise to the output. Now if you see here, from this ground to the output, it's a common gate configuration. Gate is at ground, drain is the output, and input is at the source. Therefore, this transfer function here from here to here will simply be Gm times Rd. I've ignored R0 here, I've assumed R0 is infinity, otherwise it will be slightly less than that. But if you directly calculate it, assuming R0 as infinity, it's going to be Gm times Rd. So I've applied VGN, that's your gate to source voltage, and so you'll have a current GMVI flowing from source to drain because your source potential is higher than gate. So you'll have a current flowing from source to gate of value GMVGN. That flows into the resistor RD. So you have a voltage drop of GMRD into VGN. And the gain therefore is Gm times Rd. So now the signal here at the source, if you have some unwanted signal on the ground, some noise on the ground, that sees the same amplification as the input signal. So your output signal will actually be minus of GMRD times Vi plus GMRD times VGN, this is the noise on the ground, plus Vn, this is the noise from the supply. So now we are trying to eliminate these components. So we are trying to eliminate these components. So to do that, first we need to build a circuit. We need to replicate the same amplifier circuit, an identical version of it. And they both should share the same supply. The supply and ground are common for both these circuits, for both the amplifiers. Now, I'm going to apply an input of value plus Vi by 2 to one amplifier and minus Vi by 2 to another amplifier. Now how did I get this plus and minus Vi by 2? I'll answer that in a few moments. But let's assume you have plus and minus Vi by 2 available. So then I'm going to apply plus and minus Vi by 2. To show what I'm accomplishing with this circuit, I'll try to illustrate it using a block diagram. But just to quickly say that if I have, since the supply is same for both and ground is also same for both, if this node voltage, if I want to try the transfer function from this node to this node and from this node to this node, it's going to be the same. Similarly, the ground noise from the ground to the output and the ground to the other output is going to be exactly the same. In fact, I can easily write, since I've just derived the transfer functions for them, so I can directly write the contributions from supply and ground is going to be Vn plus GMRD times VGN. So this is the VGN is the noise on the ground, Vn is the noise on the supply, so it's going to be Vn plus GMRD times VGN. Similarly, the voltage here is also going to be Vn plus GMRD times VGN. So now I'll illustrate that using a block diagram. So these are two identical amplifiers, and here I've modeled the noise as an external additive noise, and both the noise for both these amplifiers are identical because the source of noise is same for both, and the transfer function that they are going to see in both the amplifiers is also same. So I've written the noise here as the common noise. It's getting added to both the amplifiers. Now what I'm going to do, I'm applying plus Vi by 2 to one amplifier and minus Vi by 2 to another amplifier. So the output of this amplifier here, it's going to be A times Vi by 2, and here it's going to be minus of A times Vi by 2. So after the noise getting added, what you're going to receive at the output of these two amplifiers here will be A times Vi by 2 plus Vn and minus A times Vi by 2 plus Vn. Now all I need to do, if you see here, if you see here at the output, the noise Vn, it's added to both the outputs. Both the amplifiers output, the noise is just added. Now I'm going to subtract the two amplifier outputs. If I subtract the two amplifier outputs, the gain, the signal part, because this is negative here, it's going to get added. So you'll have 2A times Vi by 2. It's Vi by 2 minus Vi by 2, so you will get plus Vi by 2 plus Vn minus Vn, so there is no contribution from the noise here. So I'm going to call this signal Vn because it's common to both of them as a common mode signal. And this signal, I'm going to introduce a new word here as a differential signal. A differential signal is one, I can call two signals as differential signals if they are 180 degrees out of phase. So to be more precise, since we are going to use this nomenclature throughout this course, I'll assume that I'll say that the DC voltages are also same for both of them. But the signal levels, if this goes to Vp, this should go to minus Vp. The other signal should go to minus Vp. It should be exactly 180 degrees out of phase. Then these two signals, I'm going to call them as differential signals. If you can generate, see, generally if you take a microphone, it's going to be a single-ended signal. So meaning what I'm speaking right now, if I apply it to a microphone, it's going to convert it to a voltage signal with respect to some ground. But these differential signals are differential with respect to each other. So with respect to some common ground, there can be some common ground in the circuit. When this output goes positive, the other output should go negative. So then I can call these two as differential signals. How do we generate that? I'll discuss it very briefly. But let's assume we can in theory generate signals of this type. I have a signal Vi generated here. From Vi, I'm going to generate these two signals with some same DC value, but two signals with opposite phase. If I can generate signals like this, then I can apply it to two identical amplifiers with plus Vi by 2 to one and minus Vi by 2 to the other one, and take the output as the difference between the two amplifiers outputs. So then I'm going to say the output is also taken differentially. I don't care about the node voltage here, but rather the difference between the two voltages is what that matters to me. I'm going to call that as a differential voltage. If I take the output differentially between the two terminals, then I can eliminate all the common mode noise. So I'm using the word common mode. It's nothing but noise which is common to both the amplifiers and a differential amplifier. So this amplifier, which is built using two identical amplifiers, it's called a differential amplifier. Now to distinguish it from the previous amplifier here, this is what we call a single-ended amplifier. And the signal here, the input signal Vi, which is derived from a microphone, we are going to call it as a single-ended signal. And the amplifier here is a single-ended amplifier to distinguish it from a differential amplifier. Now you see the obvious disadvantages in a differential pair is that you have twice the area because you're building another same amplifier, identical one, and you're going to burn the power, the same power as in the other amplifier as well. So the power is doubled, area is doubled, but it comes with a huge advantage of the common mode or supply and ground noise rejection. I could completely reject supply and ground noise if I can take outputs differentially. So that's what I've shown here pictorially, what a differential signal looks like. A single-ended signal, if it goes, a single-ended signal will normally, so far we have seen a DC signal and an AC signal riding on top of it, which is what we fed to an amplifier. We called it biasing and all of that. So there was a minimum DC necessary so that it can be fed to an amplifier. So we called it AC coupled signals. Okay. And we saw that in any amplifier, you had a certain DC and an AC signal riding on top of it. In a differential amplifier system, you will see that the DC, the output of the two amplifiers in a differential amplifier, the DC will be the same, but the AC signals will be perfectly 180 degrees out of phase and their magnitudes will be exactly the same. Now very briefly, I'll discuss how to generate these signals differentially, how to generate differential signals starting from a single-ended signal. So shown here is one very simple circuit to do that. So what I'm going to do here is that I have taken two identical circuits which are going to operate on the same supply voltage, and I'm going to feed the input signal Vi to this with some DC, VDC, and similarly I'm going to feed a same signal here with some VDC, this can be a different VDC1 plus Vi. See, if I have Vi, I can always generate Vi by 2 from it, so I'll feed Vi by 2 to both these amplifiers. If you see here, I'll assume for this analysis lambda is 0, so R0 is infinity. If you see this amplifier, this is a common drain amplifier. In a common drain amplifier, if your R0 is infinity, so then the lower transistor here, if you see the lower transistor, I'm drawing this circuit here. So the lower transistor, gate is at AC ground, source is also at AC ground. Therefore, the output resistance will be R0. Since R0 is infinity, I can show this as though the output node is floating. So the small signal voltage is Vi here. I've shorted this node. So the small signal node voltage is Vi. And the output here is going to be Vi by 2 itself. It's a source follower. So source node voltage will exactly follow the gate. If your R0 is infinity, that perfectly holds fine. The other circuit on the other hand, I am feeding an input to the gate of a lower transistor, and output is at the drain here of the lower transistor, and the upper transistor gate voltage is fixed to the same DC voltage as I have applied to the transistor here. So I'll call it VDC. If I apply it there, I'll similarly perform a small signal analysis to calculate what is the voltage gain from here to here. So you can see that this is a common source amplifier with the upper transistor acting as a load. The impedance looking into the source terminal is 1 by Gm. Since I've assumed R0 is infinity, it's 1 by Gm. I'll assume both these transistors are biased with similar currents and same overdrive voltages. So the W-L ratios are also same. Then I can write the voltage gain here will be minus 1. So the output voltage here, it's Gm minus of Gm times 1 by Gm, which is minus 1. And the output voltage here will be minus Vi by 2. So now I've generated a differential signal using a MOS based amplifier itself. So this will be Vi by 2, this will be minus Vi by 2. And you can see that since I'm applying VDC at the gate of this transistor, the DC voltage here, it's going to be plus VDC minus VGS of this transistor, the quiescent VGS. And the DC here will also be same. Since this is VDC, it will be VDC minus VGS Q. So I'm using same DC currents in both the arms. So the VGS will also be same for both. I'm going to call this term VDC minus VGS Q as VCM. Then what I have generated here is simply Vi by 2 plus VCM and Vi by 2 minus VCM. Now you should quickly think about it that it's not just input that is getting amplified. What if there is noise on this supply? What if there is a noise here? Is that also not getting amplified here? Yes, it is also getting amplified. So now if you see here, what you get here is from the drain to this node. The drain to this node, you'll have to find out what is the transfer function from the drain to this node. If I assume R0 is infinity, then even though if I am changing the drain voltage, there will be no change in the drain current. So therefore I can intuitively say that there will be no change in the source terminal as well. So I have inherently built a circuit that can completely reject the supply noise variations. But in practice, if I assume finite R0, you will get some transfer function of this type, 1 by 1 plus Gm R0. But there will be some component here. So Vn by approximately, this is an approximation. It will be approximately 1 by 1 plus Gm Vn by 1 plus Gm R0. And this voltage will also be Vn by 1 plus Gm R0. So what you will receive is some alpha times Vn, some constant times Vm. I am calling it as alpha. Alpha here being 1 by 1 plus Gm R0. But if you look at this block diagram, if you look at the previous block diagram that I have discussed here, in a differential system, if you add some same noise here, so I am going to call it as alpha times Vn here. And if I am going to pass it through the same amplifier here, at the output, it's going to get cancelled out because I am subtracting the two outputs. And the polarity of the inputs, the signal here from the supply, the noisy signal from the supply is same for both the amplifiers. So that's another important property of a differential amplifier is that the differential amplifier will not respond to, so these two signals are called common mode signals. They are common to both the amplifiers of the differential amplifier, and the differential amplifier will not respond to that. It will not generate any voltage in response to that. If you take the output differentially, it will not respond to that. Okay, so I'm sorry, it's plus VCM minus Vi by 2 here. Yeah. So that's why we don't have to worry about the signal here generated because it will look like a common mode signal. The other more popular way of generating a differential single-ended to differential signal is what we call using a balanced transformer. A transformer, or what we call a balun. Balun is nothing but a balanced to unbalanced or an unbalanced to balanced converter. So these are the terminologies which were borrowed from radio frequency circuits. And so balance generally means differential signals. But by then, the idea of generating differential, opposing phase signals was well developed because there was already a rich literature in the AC power transmission. So from that, we could directly use a transformer with a center trap transformer. So where we could apply a voltage at the center trap transformer. Let's say I apply a ground voltage here, apply the center trap to a ground. terminal connected to shorted to a ground terminal. Then the voltage between the output and the ground will be Vi by 2, and the other terminal of the center tap transformer to the ground will be minus Vi by 2, so that the overall voltage between these two taps or these two terminals of this transformer will be Vi. So it can naturally generate a differential signal. Now instead of holding this common or the center tap at ground, if I hold it at a fixed DC potential VCM, so you understand a transformer, it's just a coil wound around a core, a low resistance coil wound around a core. So the DC, if I apply a DC voltage at the center, that will be the same here and here as well. So this will also be a DC potential of VCM, this will also be at VCM, but AC will be different. So it will be VCM plus Vi by 2 with respect to this, and here this will also be VCM plus minus Vi by 2. So this way I can generate differential signals using a balun. So then typically the way in which we would do the processing, differential processing, is that if you, let's say you have a single-ended source, I've shown this as a source here which generates a single-ended signal, I can use a balun or some single-ended to differential amplifier which will convert or generate differential signals, and I'll use these differential signals and feed them to a differential amplifier. Instead of a single-ended amplifier, I'll feed it to a differential amplifier. And finally, let's say the load to which you are finally driving it can be an audio speaker which you are going to drive it. Let's assume it's a single-ended load, meaning one node is connected to ground, only one node is accessible, so then it's a single-ended load. In that case, you have to feed a single-ended output. Whenever we talk about a single-ended output, you will have one node and the other node will be ground. So I have to generate a single-ended signal finally before I'm going to deliver it to the load. I can use what we call a differential to single-ended converter. Okay, that will convert a differential signal which will take, whenever I say differential signal, it's usually two signals with same common mode but exactly 180 degrees out of phase. So these two signals are called differential signals. So it will take a differential signal as an input and generate a single-ended output, and that output can then be fed to the load resistance. And that D2SS ground, the ground of the differential to single-ended, will be the same as the ground of the load. Okay, so this comes with an advantage. So far we have discussed about differential amplifiers. One of the main reasons is that the differential amplifiers will not react to common mode changes. So I'm calling right now the ground and the supply noise as common mode changes. The differential amplifiers are not going to respond to that. That's one huge advantage of a differential pair. We will see, as we discuss probably the differential amplifiers in the upcoming weeks, a lot more advantages and how they evolved over time, and their penetration into the integrated circuit operational amplifiers. So that's what will be the topic of the next few lectures.